thank you very much for coming. Today it's our immense privilege to welcome Professor Mark Lancaster. He graduated from Oxford, then he moved to the US and was working on very important practical physics for nearly 20 years.
Near 30.
He was spokesperson of G-2 experiment in Fermilab, which is one of the most important experiments in particle physics generally, I would say. And also has been collaborating on Mu2E experiments and other projects, for example, DESI and so on. So please, huge applause for Mark.
Thank you. I should say I'm going to try and keep, I don't mind if you ask questions in the middle of this, right, and whatever, right, if you don't understand something or you need something explaining, feel free to ask questions. I thought I'd start, given that I'm in this august surroundings of Cambridge University, to just remind you of all the great tradition, given that I've come down from Manchester today, just to remind you of the great tradition of Manchester physicists arriving in Cambridge. So basically you've got 100 years here of Cavendish professors of physics at Cambridge who all started their careers in Manchester, arguably did some of their better work in Manchester, certainly in Rutherford's case. Young J.J. Thomson was born in Manchester and went to university in Manchester aged 14. He was one of these horrible child prodigies who was good at absolutely everything. Lawrence Bragg wasn't there very long. Neville Mott was. And then there's a couple of Nobel Prize winners, three Nobel Prize winners who ended up in Cambridge. Patrick Blackett, who's probably the best looking person here, right? This is Blackett, right? Possibly Lawrence Bragg. He's quite a good looking lad, right? And Blackett's the only one who moved from Cambridge to Manchester, and then he ended up at Imperial College. Which then brings me to the only real claim to fame that I've got in physics is this, which is my PhD academic tree, which I researched during COVID. You know, when you're bored in COVID and you just keep going down Wikipedia page after Wikipedia page. And then I harangued my supervisor and his supervisor to find out who their supervisors were. And so I've got this strange lineage which I can trace back through various strange Cambridge people, essentially all Cambridge people, back to Newton. And then you've got this august bunch of people like Kelvin, Maxwell, Stokes, Darwin, Oppenheimer I'll come to in a moment. The sad part of this is actually it's taken about the best part of 400 years for a female to appear on this chart, right? So that is, thankfully, that is changing, right? I've had like 3 or 4 female students. Claudia was my last student. So I'm going to begin with Oppenheimer because he's one of my heroes. He's also, I've got a claim to fame that I've urinated in his toilet in Berkeley. I don't think it was his original toilet, but certainly in his apartment. So that's one good claim to fame. So he was, obviously a great person, and he was involved very much in it was basically a random walk for the discovery of the muon, right? The muon was, they knew it sort of existed because they were seeing things in cosmic rays, but they had absolutely no idea what it was. And so at one point, they had no theory to explain why it was so penetrating compared to the electron. So at one point, Oppenheimer had the idea that he was going to develop a theory called red electrons and blue electrons. The red electrons were our normal electron friends, and the blue electrons were the muons, because they didn't have any theory. All they had was basic electromagnetism. And of course, by and large, Millikan, of famous E over M fame, right, was basically I should be careful what I say given it's being recorded, was basically a crook, right, who somewhat manipulated his data. But he sent his PhD student out to find these muons and look at them properly in the cosmic rays. And because he was convinced that these muons were photons, because he was religious and thought they were to do with he had this theory called the birth cry of atoms. So anything coming out of the universe was basically photons, and so he was convinced muons were photons, but they couldn't be because they didn't obey any of the equations. But anyway, he forced his PhD students to go looking for evidence that these muons were photons, and of course he didn't find any evidence for it. But while he was doing that, he discovered the positron. So Anderson discovered the positron because his PhD supervisor told him to, prove that muons were photons, which of course they weren't. So this drove Oppenheimer to absolutely to despair. He was certainly a man whose glass was probably half empty rather than half full. And I think this is the only picture I've seen of a physicist looking cool with a hat and a cigarette. So it's certainly a good thing. So things have actually improved since Oppenheimer's time, just a little bit. I mean, you know that we have this standard model of particle physics. It's got these families of particles, of leptons and quarks and the bosons, the photon mediating the electromagnetic force, the W and Z mediating the weak force, the Higgs boson and the gluon. But of course, it's not great because it can't explain essentially two of three things. It can't explain the galaxy rotation speeds, for which we need dark matter, unless you believe that gravitation has been modified in a strange way. And it can't explain why the universe, why all the antimatter disappeared at the start of the universe and we're in a matter-dominated universe. So that's a big problem of the Standard Model, despite its many successes. And then it gets worse when you look at it in a little bit more detail, in that it's largely unnatural, right? In most theories that you do, so for instance, if you look at chemistry or say nuclear physics and things like this, typically the ratios of the masses or the energies or the things that you're dealing with are within factors of 10 or so, right? That sort of theory seems to be quite natural in that respect. But many of the numbers in particle physics have horrible magnitudes in them, like the ratio of the lightest particle in the Standard Model to the heaviest particle in the Standard Model is about 10 to the 13. That's a problem. The Higgs mass to the Planck scale, it's believed that, you know, if the Higgs is the last particle we discover, it's 10 to the 17. If you believe that the Higgs boson is responsible for dark energy, it's off by 10 to the power of 120. And we don't observe parity violation, the strong interaction, so that appears to be fine-tuned at 1 part in 10 to the 10, right? So all these are very unnatural things, and then we have these other questions, right? What is dark energy, etc., etc. So we've basically, particle physics, despite its successes, I would say it's in a bit of a mess, actually. So the whole idea was we built the LHC. It started taking data about 15 years ago, and the idea was as soon as you turned on the LHC, you're going to see this amazing plethora of new particles of all these exotic supersymmetric theories or string theories or whatever. And this plot is now impossible to find on the internet because it predicts what the LHC would have found with the new particles from supersymmetry compared to the Standard Model. And we should have been swamped with these supersymmetric particles. And then as soon as the LHC turned on, and that didn't turn out to be the case, all these types of plots disappeared from the internet rather quickly. The theorists rapidly backpedaled. But any time a theorist makes an outlandish statement, I save the plot in a file somewhere in my Dropbox folder, etc. So at any moment in time, I can always reproduce what they said 20, 30 years ago to embarrass them. So we've essentially got this problem that we should have seen all this new physics by now at the mass scale of about a TeV, so 1,000 GeV, and we haven't. So my view really is that we should try and do more measurements and a greater variety of them, and maybe not hope per se that things are going to show up at high energy. So that's typically how we've evolved in particle physics over many years. We've had two approaches. One is basically to have high energy particles. You rely on E equals mc squared. If you have enough energy, you can create enough mass, you'll create a new massive particle, right? That's relatively straightforward. The other way of doing it is to rely really on Heisenberg's uncertainty principle, and you'll know that you can essentially violate conservation of energy momentum, or you can borrow energy for a certain amount of time dictated by the uncertainty principle, and essentially in that small amount of time, anything goes. So you have these virtual particles which then actually create real effects. So the effects, for instance, on a muon is to change its magnetic moment, which is what I'll be talking about. But these effects tend to be absolutely tiny. So it's typically at about the 1 part per million. So I would argue that in general, if you look at the history of physics over enough years, we've probably had as many breakthroughs by trying to measure things very precisely and confronting it with the theory and seeing that it doesn't quite agree, as we've had by just going to high energy and going, right, let's try and create these things. So there are many examples. Even in general relativity, for instance, the tiny deviations in Mercury's orbit were basically a precision measurement which vindicated general relativity. So important in this really is this concept of virtual particles. What I'm really going to be talking about is a muon interacting with a magnetic field, principally the spin of a muon, the quantum mechanical spin of a muon interacting with a magnetic field. A magnetic field is just a photon to us particle physicists and in quantum field theory. So you have this sort of top diagram here. This is the simplest diagram you can draw of a muon interacting with a magnetic field. But you can also pass virtual particles between these two muon legs, and you can essentially, during the time the uncertainty principle allows, have any particles in there, and they have a measurable effect. So typically the standard model virtual particles affect this magnetic interaction at about the 0.1% level. The things that we're interested in, say, beyond the standard model particles, will typically affect it at a much smaller level, about 1 part per million. So that essentially means that we've got to measure a quantity to 1 part per million, which is a very precise measurement. So the word precision, this is what I'm trying to orientate you. Just think about, I'm going to talk a lot about parts per million or parts per billion in terms of measurements, and you're used to your undergraduate labs measuring something to 3% or 10% or whatever, right? And our particle physics and astrophysics colleagues are not immune to that sort of thing, and they talk about precision measurements all the time. So this is just a selection of papers from about the last 6 months of people claiming in particle physics and astrophysics to have made precision measurements. So we've got one here which is at 14,000 parts per million, 9,000 parts per million. There's an excellent measurement here from CMS which is at 120 parts per million. So essentially the measurement I'm presenting is about 1,000 times better than the best of this assortment. So the word precise is somewhat overused, I would say. So magnetic moments, I guess you're sort of familiar in some ways with magnetic moments from just basic electromagnetism, in the respect that if you have loops of current, that essentially creates a magnetic moment. So a rotating charge will create a magnetic moment, essentially from its intrinsic orbital angular momentum. But we also know that in quantum mechanics, a particle has L numbers and S numbers. This is also, this is true of all your atomic transitions. So all particles have an intrinsic spin as well as an orbital angular momentum. And that intrinsic spin also can contribute to the magnetic moment. And essentially you have this very, very simple equation. This is what Dirac came up with in the late 1920s, that the magnetic moment due to the spin is just related by the charge 2 over the mass and then this magic number g, which Dirac predicted to be exactly 2. There was then a very long history of trying to measure that and prove that it was true, well, it was 2. And there were then lots of problems in the measurement and the theories where people started putting in factors of a half and various other things. But eventually everybody agreed that Dirac was right. I mean, how could Dirac possibly be wrong? And that this number was basically 2 in the simplest possible model that you can write down. An important thing that does happen, though, is if you place this spin in a magnetic field, so if you have this magnetic field this way, maybe the spin is this, it will precess around at a certain very well-defined frequency. And you have a torque due to the magnetic moment when you're in a B field, and that causes the spin to precess. So it's the usual equation of a torque, and the rate of that precession is directly proportional to G. So that essentially gives you the mechanism to measure G. So it's exactly like the torque that you have when you're in a gravitational field of a gyroscope and it just precesses around. So the quantum mechanical analogy is if you take a muon or an electron or whatever and it has a spin in a certain direction, that spin will precess around the magnetic field at a very well-defined rate. And that's what we're trying to measure. Of course, the whole concept of spin, you may have heard of the Pauli spin matrices, now it's an accepted concept of quantum mechanics, but it took the best part of 20 years for people to really believe in it and what the effects of spin were. And Pauli, of course, was, despite the fact he's got these spin matrices named after him, he actually didn't believe in spin at all. And Pauli is just great for producing phrases. So if he didn't have the theory and anybody else did, he would rubbish it and just say that it was nonsense, right? So he also had a great thing where if he went into any room with experimental apparatus, the apparatus would stop working. So they've got a new room named after him in CERN, you know, where people go, we're not putting any apparatus in there because it will go wrong. They've actually just been donated Pauli's Nobel Prize medal, which is in the CERN library at the moment, actually, if you're ever in CERN. So, of course, Pauli ridiculed the whole thing that electrons had spin, but then it was proved that they did, and this then produced this great quote that Pauli, the deity does not extend to the self-styled vicar on earth. So they were calling, because Pauli thought he was basically God's gift to physics. So these are two of my favourite pictures in physics. This is the great Pauli with a dislocated or broken shoulder, which he couldn't tell anybody he'd broken his shoulder because he got it while he was in Michigan during American Prohibition when you weren't allowed to drink. Of course, he did drink, got drunk and fell down the stairs and broke his shoulder, but he couldn't tell anybody how that had happened because it was illegal to drink at the time. And as far as I know, this is the only picture of Dirac with an axe. I mean, Dirac was a very demure man, right? This is taken in Princeton. I don't know why he had an axe, because I've never quite got to the bottom of why Dirac had an axe, but I do like that photograph of Dirac. So this I'll come back to in a moment. This is more from Pauli. So, of course, eventually they decided that the electron had spin, and so it would have this G number of 2. And so they went, well, what other object do we know of which has a spin of a half? And everybody went, the proton. And they went, so what is the proton's G factor going to be? And Pauli said, this is obviously a complete waste of time. There's no point even measuring it. It's a spin a half particle. It'll be like the electron, but you've got this factor of 1 over m, so it'll just be smaller by, you know, the mass of the proton to the mass of the electron. And thank God Stern and Gerlach of the Stern-Gerlach effect basically said, all right, let's not do that. Let's actually go and make the measurement. And Stern actually was in the lecture theatre and made all the theoretical physicists write down what they thought G was going to be. And nearly all of them just wrote down, well, obviously it's going to be 2, right? They then measured it, and it turns out to be 5.7 or something. And actually that measurement was quite lucky, because you see Stern here, he's a bit of a maverick, you know, there he is with a cigar. And in the Stern-Gerlach experiment only worked because the photographic plates and the silver atoms were going on were just caked in his cigar smoke, so you could actually see what was going on. Otherwise, that wouldn't have worked. And he's got this great quote: "You do less damage if you let something fall than if you try to catch it." And this is my favourite quote. So Gerlach, of course, was said in a riposte to Pauli, essentially going, "No experiment is so dumb that you shouldn't try and do it," because Pauli has said it's a waste of time to do it. Anyway, so Stern, I think, won some money on that particular bet. So I would argue that the measurement of 2 magnetic moments has arguably changed most of modern physics. So the fact that the magnetic moment of the proton and then the neutron wasn't exactly 2 is largely due to the fact that the proton and the neutron have things inside it. They have quarks. The electron, as far as we know, doesn't ostensibly have any substructure, so it has this G of 2. It just has these virtual corrections. Whereas the proton and the neutron are composite particles. So this evidence that the proton and the neutron had things inside them, quarks, is 30 years before anybody even thought about quarks or let alone discovered quarks. Also then in 1947, the great and the good all sat around in outside New York. Is Oppenheimer. That's Feynman being really annoying to Schwinger. That's Schwinger there, I think. So Schwinger derived these virtual corrections to the G equals to 2 and worked out that these corrections were basically alpha over 2 pi, right? But that calculation was 11 pages. Feynman did it in about half a page, and this is him being very smug and showing everybody, I've done it in half a page. And you know, poor old Schwinger was a bit annoyed. Oppenheimer's looking on like the great man he was, right? And they're all just crouched around. So this is on Schwinger's grave in Boston. It's essentially impossible to find. It took me an hour to find the grave. This is my friend here who was a banker. He finally found it under the undergrowth, so we could take this little picture of Schwinger's grave. One of the great graves with equations on. You've got Boltzmann. Ohm's is terrible, right? It's a really terrible grave. Boltzmann's is pretty cool, but so then you might ask, right? How on earth do we measure how the spin of a muon processes in a magnetic field? Because it's very difficult to measure spin. It's essentially intrinsic quantum mechanical property. And of course, the muon has the property that it decays. It's not stable. It decays at rest in 2.2 microseconds. But the lucky thing is it decays by the weak interaction. And the weak interaction has certain spin or helicity, chirality properties, which essentially means that when the muon decays, the highest energy positrons from a positive muon are going in the direction of the spin that the muon was pointing in. So then that is really lucky, because essentially due to this property you can go, aha, if I just measure these positrons in a certain direction, I know the spin was pointing in that direction. So arguably you could just sit there and you go, right, electron going there, and then just count the rate that the electrons arrive in a certain direction, because the spin's going around. So at some point it will start hitting it, and then it won't hit it because the spin's pointing in a different direction. It's going around. So you just sit there and essentially just count these things. So that's a really lucky thing. And also the muon, 2.2 microseconds, sounds like a short time, but if you have these at a reasonably high energy, you can Lorentz boost it, and we boost it to about 64 microseconds, and in particle physics times, that's essentially an eternity, right? So it's easy to measure things for that time. So as I said, you've essentially got this rather simple setup. You've got this spin whizzing around, and this is very, very simple, really. We've got so you put the particle in a magnetic field. If you put a particle in a magnetic field, you know that you've got this QV cross B, and you know that is balanced by the centripetal acceleration. So you've got a very simple equation, and you can then work out exactly how long in a magnetic field it takes the particle to go around in a circle, and that's called the cyclotron frequency. And we can also work out, we know how rapidly the spin processes. It's essentially given by this G number. And we can and then if we take the difference between these two frequencies, the frequency with which it goes around, the momentum essentially is doing one period, and the spin is doing one period. Those are slightly different. They would be exactly the same if G was 2, right? So the spin would process at exactly the same rate as the momentum, but G's not quite 2 due to these virtual effects, and the difference in these two frequencies allows us to measure G minus 2, effectively. So that G minus 2, this difference in frequencies is this G minus 2 over 2 times the magnetic field over the mass of muon, and then E over C, right? So it's a relatively straightforward setup. So you can see that here in a cartoon. You can see the momentum vector in blue. Obviously, it's just going around in a circle. It's going around, guided by the centripetal force of the magnetic field, and the spin is going at this is exaggerated, the spin's moving at a slightly different rate. So you can see at some point, say here, the spin's all pointing inwards now. So we'd expect a load of positrons to arrive when the spins are pointing inwards. So if we had detectors on the inside, and then sometime later, this spin is all pointing outwards, so all the positrons are going away from our ring, and we don't detect them if we have detectors on the inside. So what we expect to see is that if we have detectors on the inside, we just see the number of positrons going up and down at a rate which is essentially determined by this G factor. And that is particularly true, as I said, because this property is when you select the highest energy positron. So you just see here, this is just an energy spectrum that we have from our data of the number of positrons being detected, and you can see it just essentially just going up and down. It's just going up, down, and this frequency is a beautiful frequency. And obviously, the number is going down over time because the muons are decaying, so we have fewer positrons just from that. But that's essentially what we're trying to measure. So, of course, they had this idea, years ago. The first experiment ever conducted at CERN was the G-2 experiment, and they basically proved that it agreed with Schwinger, that it was alpha over 2 pi, and everybody went, right, we're done, Schwinger and Feynman are correct, QED is the great theory, it's alpha over 2 pi, let's move on, right? So obviously the head of CERN theory at the time said, then the experimentalist, the good old experimentalist said, well, why don't we go and try and measure it a little bit better? And then, like Pauli, the theory guy said, it's not worth it. We know what the answer is. It's alpha over 2 pi. Don't bother measuring it. But luckily, this man here, where are we? In the great suit I'll come to later, Francis Farley, actually an alumni of Clare College, Cambridge, said, no, don't bother, I'll go off and measure it. So Farley, and this was the entire experiment, right? This is like 5 people went off and measured it. And lo and behold, it wasn't alpha over 2 pi. It was slightly bigger than alpha over 2 pi because as well as the electromagnetic interactions in the virtual loops, you can have interactions from the strong force, from quarks, and principally from quarks, and that increases the number higher. So then they had a little bit of credibility and said, right, let's go and measure it again. So this is the first one with 5 people, then 10 people, which proved the strong force existed, and then 20 people measured it again, and they were doing well, right? The precision in parts per million has come down from 10,000 to about 10 parts per million. And then what happened here was obviously the motivation was then to start looking for new particles, which might be particles beyond the standard model. But with this precision, you could only really probe particles of up to about 35 GeV. And the colliders started to probe particles at 100 GeV. So unless they could significantly improve the precision, it wasn't worth improving. And then it gets difficult. So this path was relatively straightforward to get to 10 parts per million. They increased the number of people by 5, and you can see this is then going out here and getting harder. And then we stepped in here and got it out here. So this has got progressively more difficult and required more and more people. I would say the principal reason for this that is, well, basically to do anything difficult, you need more money. Money's difficult to get. You need more people. You've got to convince them to do a crazy measurement. Not many people want to do crazy measurements. And then there's also Brooks' law, which basically says that if you throw more people at a problem, it might get worse. So it doesn't necessarily solve all your problems. So we're a collaboration of about 200 people compared to the LHC. There's about 7,000 people working on the LHC. So I showed you this equation. Obviously, life is not quite that simple. Some of you, one of the few books that puts terror into my soul is Jackson's book on classical electrodynamics. However, it's an amazing book, and he has the real derivation of this. So you can see this is the simple term. But there are other effects, because if you just put a set of muons into a magnetic field, what they will tend to do is defocus vertically, and they will just hit the top of your ring, and they won't go around. You need them to go around a few hundred times, so they just disappear. So you need to focus them, and the way you focus them is with electric quadrupole. And as maybe you know, in electromagnetism, if you have a velocity beta and an electric field, it essentially acts like a B field, so you get this correction. And also, we would like our muons to be going exactly like this in a vertical magnetic field, but they're not. They've got a slight angle to them. So that also introduces another term here, and of course, Jackson derives all of this. So that's the real equation. So this is the set of characters who set off to try and make this measurement. There's about 200 of us. This is we started off in about 2011. In the UK, everybody said I was insane to want to do this, but I managed to convince about 10 people to do it in the UK. This is a February in Chicago, which looks absolutely beautiful, nice blue sky, but it was about minus 20 degrees, hence all the coats. But this is our lovely building where we did the experiment. We weren't out there very long for the photograph. So one of you asked earlier how you produce muons. It's not very sophisticated. All we do is we have a linear accelerator of protons, and that gets accelerated to about 1 GeV. It goes into this accelerator, which accelerates them and bunches them to about 8 GeV. Then we whiz them out to this even bigger accelerator, which bunches them again and makes much more intense bunches. This is an old accelerator that discovered the top quark. And then they come back in here, and then they hit a target in here. And when they hit a target, they produce pions. Those pions decay we need, as I showed on this previous equation, we need a cancellation here, right? Essentially, we want this term to be 0, which you can get by having a gamma factor or the momentum of the particles being exactly 3.094 GeV. So we have to select pions which are a little bit higher than that, which then decay to the muons. That's a bit of a saga, but we do that, and then they whiz off and they come into our building here. Basically, it's muons with no pions, which is great news, because pions are annoying. So they come here. This is in more detail, but the target is here, I think. And then once they've produced the pions, we let them whiz around here a few times, such that all the pions have decayed, and then eventually the muons whiz off into here. So then they arrive into our hall, and they come in here. We focus them with some quadrupoles, and they enter here. So this is a very strange experiment, because most particle physics experiments, you collide particles into each other, or they hit a target. We don't do anything. We just let the muons come in, and we let them decay, and we watch them, and that's it. So it's a very unspectacular particle physics experiment. But obviously it's not quite that easy. You can see here the view of the particles coming in through these quadrupoles, and then they come in through the back of the yoke of the magnet here. So essentially, we inject about 10,000 muons at a time, and it's a very inefficient process because we have to have these muons of a certain momentum, and we need 10 to the 12 protons to get 10,000 of these. So what's that? 10 to the 8, right? So we get 10 to the minus 8 muons out of this. So it's a very inefficient process. And we measure these decays for about 10 milliseconds, ostensibly for about 8 months of the year, 24 hours a day. And we produced about 500 billion muons. So is it the world's biggest number of muons? I don't know. But anyway, we analyzed about 310 billion of them. So then we have a bunch of problems. So the first problem is, our muons sort of come in at this particular angle, and then if they just encountered the magnetic field coming in at this angle, they would do something like this, and they would just disappear, which is then bad news. So what we actually need to do is to let them come in and get to the middle of the magnet, and so we have to cancel the magnetic field of the magnet in this region by having essentially an anti-magnet with a field in the opposite direction, which is this horrible device here. It's a sort of a little small superconducting magnet, but that allows the particles to come in. It provides an opposite 1.5 Tesla magnetic field. So then we've got them coming in, and they're nearly where we want them to be, but not quite. They come in here, and again, if they're not in the center, eventually they would spiral out and we'd lose them. So what we need to do is when they get round the first time at 3 o'clock, we need to give them a little magnetic kick to get them in the middle. So, and a magnetic kick sounds quite easy. Go away, just turn on a little magnet. But obviously, this takes 149 nanoseconds for this to go round. So this kick's got to be very quick, right? It's got to be sub 100 nanoseconds. And to produce even a relatively small magnetic field requires a huge rapid voltage, essentially, right? So we need to provide a huge voltage very quickly in under 100 nanoseconds. And if any of you have tried to do that, you'll realize that it's not straightforward. You've essentially got to provide about 150,000 volts in 100 nanoseconds. And the way you do that is you essentially charge up a giant capacitor. The giant capacitor is basically some castor oil. We charge that up and then discharge it very quickly and send that pulse in, and it creates essentially this magnetic field, right, of this pulse. The problem then is it creates these after pulses, which then kick the particles again when they come around the second time. So we have to understand that. It comes in, this pulse comes in on these giant cables, which causes no end of problem, because you can imagine sending 55,000 volts in a short space of time. You need some pretty robust cables. They would spark, didn't quite set on fire, but they would spark and then wouldn't work. And there was only a couple of manufacturers in the world that could make these cables and get them to work, and it took a lot of time to get them to work and to stop everything from sparking. The other problem, as I said, is these particles diverge vertically in the storage ring. So the only way we can focus them is we have electric quadrupole plates. So these are about 20 kilovolts, and they are pulsed. So we put an electric field on them to pulse the beam, and that essentially focuses and defocuses the particles in the two directions. And so we can keep the particles in the center of the magnet. So again, we have to provide a rather rapid voltage again to these plates, which are quite long plates. That also has problems because if you don't have a very good vacuum, things spark at high voltages. So we had a lot of sparks, and when these things go wrong, they're inside a vacuum chamber, they're very hard to access. So then you need access to somebody who's got very long arms but small hands. Those people are very rare. Luckily, my postdoc, she had long arms and small hands, so she was wheeled in constantly and sort of pushed into the vacuum chamber going, can you reach that and move it? So she was vital to the whole experiment, actually. So you've probably heard in your physics career that essentially everything in physics is simple harmonic motion, which it basically is, right? Because if you pull a spring, it rocks backwards and forwards. So if you have any restorative force, it will invoke simple harmonic motion. So here we've got a restorative force from the magnetic field and a restorative force from the electric field. And so essentially our particles are moving in and out radially, slightly, and up and down radially, a small amount, in beautiful simple harmonic motion, right? And how we measure that is, this is where the UK came in. We made these detectors which sit inside the vacuum chamber. These are very thin aluminized mylar straws with a gas inside them at high voltage. When the positrons go through it, we can detect them with this in all these various planes of detectors, and we can work out the trajectory very precisely, and so we can work out where the positron originated from and get a profile of the muon beam, and this is the profile that we get. So it wasn't quite perfectly centered. It was slightly off-center because the kick from these giant 55,000 cables wasn't quite high enough. When we cranked it up a few more thousand volts, it would spark. So we could never get it quite at the middle, but it was close enough that it didn't really make any difference. So here you can see a cartoon, if I can get this to play. This is a cartoon of how the beam moves. So you can see it just moving in and out radially. It's also moving, you can see, vertically, and that's just in perfect simple harmonic motion. This is the radial motion of the beam. It's moving about plus or minus a couple of centimeters, and also the width of the beam changes. But largely all of this is dictated by some reasonably simple equations. So here I've got another quick video. This shows what it's like when you go. So we measure the magnetic field by something called a trolley, which is the American word for basically a little train, which we put NMR probes on it, and it goes around. But then we put a little camera on it once so it could go around and take a video. So that's the inflector. These are, where are we now? Where am I going? It's whizzing around. These are the quadrupole plates there. No, that's the kicker, isn't it? No, that's the quadrupole plates. So it whizzes round and round and round. And you can see there's quite a lot of, no, those are the kickers, those are the quadrupoles. So there's quite a lot of infrastructure in here holding everything in place. This is basically a piece of string which pulls the thing along. It's basically a piece of fishing line which occasionally got stuck. And at some point you will see our great little, you'll see our great little trackers just protruding out. This little train we have to park into a garage when the muons are there. And then occasionally it would get stuck. So again, we needed the long arms and small hands. This is another probe that goes into the beam. I'll talk about this in a moment to measure the magnetic field. And there you can see our glorious little tracker detectors. And then it just goes round and round. So that's what it looks like in the inside. So here we go. This is what I said earlier. This is how our spin rotates with respect to the momentum, and we have this positron spectrum going up and down, and you can it actually builds up remarkably quickly. So this is real data. So in 4 minutes, this is 9 minutes, this is 5 to 100 microseconds, 100, you can see here we haven't got many particles because they've mostly decayed, but the particles that we're looking at in the first 100 microseconds, you can already see a very pronounced wiggle. So that's relatively straightforward. And actually, we're about to release the data where you can do fits of this data yourself in 4 lines of Python, right? It's basically a 5-parameter fit. It's the dilated lifetime of the muon, this frequency which we're trying to measure, a phase, and a cosine. And that's largely it. So you can get a reasonably good answer just by doing 3 lines of Python to that histogram, right? Which is a bit depressing when you've spent 10 years doing a measurement. So, but just a bit more detail on the detectors we have. Principally, our detectors are measuring the energy of these 24 calorimeters inside the ring. They're lead fluoride crystals. They produce scintillator light when the electrons go through, when we measure that in silicon photomultipliers. The other tour de force in this experiment is the magnet. So you remember that the G-2, we also need to know the magnet. We need to measure this frequency, but we also need to measure the magnetic field. And we need to measure the magnetic field very precisely, or the magnetic field needs to be very, very uniform. And so we produce the magnetic field of a superconducting coil. We have to ship that superconducting coil all the way from Long Island to Chicago via the east coast of America, and it came up through the Mississippi. That was quite a nerve-wracking journey. And then it arrived, and these are basically the pole pieces, and what they do is determine what the magnetic field looks like. And what you try to do is you have to adjust these pole pieces, which are multi-ton objects, to better than the width of a human hair, and it's an iterative process. So what you do is an American word is called a shim, which I didn't know until I was in America, which is basically just these little bits of metal which you've got a screw thread in it and you move it a tiny amount, and this moves this pole piece by microns, right? And you basically go around and tweak all of these and then go, what's the magnetic field look like? It's not great. And then you do it again, 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 and you do it for 2 years. So we had a bunch of PhD students who just went around, and all they did was tweak these things for about a year and a half. Good job if you can get it. And then we came up with an even better idea that we could improve the uniformity if we put some laminations, like this metal foil laminations, on these pole pieces. So we did a simulation and went, my God, if we put these little foil pieces on, it gets even better. But we don't quite know what the shape of those foil pieces are. So then we had to stoop even lower than PhD students and bring in high school students from the local area who would basically work just for cans of Coke, right, basically. And I actually shipped over a couple of people from the UK to help. She actually did she moved on she was a sixth former at the time, but then did an engineering degree actually here at Cambridge. I met her again a few weeks ago. And they were real slave labor, right? I mean, they were just sticking these foils on here, putting them on, measuring the field, changing the shape. They had to weigh them all. But a Fermilab engineer is charged out at about $400 an hour, right? So it would have cost us millions if we'd have employed real engineers, but these people were free, right? So without them, we couldn't have done the experiment, because it would have cost too much money. So they did an amazing job, and we produced this magnetic field of just an amazing uniformity. So we measure the magnetic fields by having probes, which are above and below the ring, so they're not exactly where you want to be. And then we send this train around with NMR probes in it when the muons aren't there to measure the magnetic fields where the muons are, and we do that every few days. And we know that it's changing in between that, but we can spot how it's changing from these probes, and we interpolate between these things. And then we need how you know absolutely what your magnetic field is then a bit difficult, because you need reference probes of somewhere where that you know exactly what the magnetic field is. So that's quite a complicated set of calibrations, and that took quite a long time. But in the end, we had this map. Again, this is where the muons are from, again, it's not quite in the center. And then this is the uniformity of the field in parts per million, right? And it's basically completely uniform apart from at the edges where most of the muons aren't. So that was a truly amazing endeavour to do that. So then we got everything. We got the field working. It looked nice and uniform. And then the beam came in, and it was a bit disappointing. Well, firstly, I was playing golf, so I missed the start of the beam coming. I thought, there's no way they'll get the beam while I'm playing golf. And then I came back, and everybody was stood around going, have we got beam? Because, it was very low intensity, and then we sort of saw this. It was like, have we got a beam? When the LHC turned on, of course, it lit up like a Christmas tree, and they all went absolutely crazy, and we're just stood around. That's the lab director going. He's going, have you got beam? We're going, don't know, really. Probably. But eventually that got a little bit better. But like all good things, after about a year, the LHC had the problem only 2 weeks later. Every experiment has a disaster. Of course, the LHC blew up, right, a few days later due to these shorts in the superconducting magnets, and went bang, and it took 2 years to fix. Because this is being recorded, I can't name the people responsible. But if you ask me later, I can possibly say. And we had a problem whereby if you have a 1.5 Tesla magnetic field, if you've ever been anywhere near a magnetic field with something magnetic, it's really surreal, because you go there with something and it starts twisting, and it's because obviously you can't see, it's disturbingly strong, right? And what you shouldn't do anywhere near a magnetic field of 1.5 Tesla is have a magnetic brick or a steel brick. So obviously, what happened was, unfortunately, we had a pile of bricks, and we had to put these bricks in front of one of the vacuum chambers, and we do that at the start of run. But somebody had been fixing some floor tiles, and we had all these non-magnetic bricks and one magnetic brick, which was somehow introduced to the pile. That was then passed to my postdoc, who passed it to somebody else, and then it flew out of their hand and went horizontally through the air and hit the magnet and quenched it. And then when a magnet quenches, it creates an enormous noise, etc., etc. So I wasn't there at that moment. I was on the way to the pub, but I was in the car in an Uber on the way to the pub, and my postdoc, who was phoned me. Well, she was in the car with me, but they phoned her up, and she was in charge of the operation at the time. And all I heard was, "Oh shit, oh shit, really, shit." And so they closed us down for 6 months. The DOE went absolutely crazy. So I spent 6 months doing nothing other than filling in safety forms. But actually, we were lucky that it could have been a lot worse. So it did actually improve things, but we lost 6 months due to that. So as I said, you can do this nice 5-parameter fit. Any of you doing undergraduate labs will be told that the only guide to anything with statistics is your chi-squared per degree of freedom, which should be about 1. When you do this 5-parameter fit, you don't get a chi-squared per degree of freedom of 1, right? So that's either telling you that you've got your uncertainties wrong, or your model's wrong. In this case, it's our model is wrong, because the 5 parameters is just a little too simple. Because that 5 parameters is not taking into account all these simple harmonic motions of the beam, which we have to take into account, essentially. So if you do a Fourier transform, essentially, of the residuals of this 5-parameter fit, what you start seeing is all these frequencies start popping up. And that's basically telling you that there are some effects which are simple harmonic, which you're not taking into account in your fit. So we then had to add about another 20 or 30 parameters into the fit to account for all this simple harmonic motion. The fit function is here. If you've ever tried to do a 20 or 30 parameter fit, it's a dark art. And then when you do that, you get this beautiful chi-squared of basically 1. This is before, when you do the 5-parameter fit with all these residual frequencies and the Fourier transform. And then afterwards, you don't have any of these residual frequencies, which basically means that you've either overfitted it or you've understood what you're doing, right? I think we understand what we're doing. So the final thing, really, that we have to do in this is, obviously, we're measuring a frequency. You can only measure a frequency if you've got a reference frequency or a clock, which is ticking at a known rate. And, of course, what we didn't want to do was be biased towards a measurement. We didn't want to go, well, we want to get this number, that number. So what we did is the clock frequency that was sent to all our electronics was shifted when it was put in the cupboard and moved by a tiny amount. And only 2 people knew what that tiny amount was, and they wrote it down on a little piece of paper. They had to do the experiment, and they could once a week open the cupboard, and just check that the frequency was still what it was. It hadn't gone crazy. And they would go, yes, everything is okay. And then they'd lock the cupboards and say, we didn't know. And that was written down on a piece of paper. So I'll come back to that in a moment. We have to make a few other corrections. It's not quite as simple as just measuring this frequency. So this is this clock frequency. We then have to make a bunch of corrections due to the things that I've essentially already said, really, that one of the things is that our muons aren't exactly at this, what we call this magic momentum. There's about a 10 MeV difference, and we have to correct for that. Our muons aren't all perfectly horizontal, which we have to correct for, and also because our muons have a range in momentum, their trajectories towards the detectors are slightly different. And I said the frequency that we're measuring is this difference between the spin frequency and the time it takes to go around the ring. And the time it takes to go around the ring is determined by the momentum. So if your momentum is different, then the time it takes to go around your ring is different, and so you get a change in the frequency. And so we have these corrections essentially due to that. They're not particularly large. Just to orientate you, our measurement is 127 parts per billion. So these are larger than our uncertainty, but they're known very well. Right? We also have to make corrections to the magnetic field, the couple of effects that we have. This is our amazing giant capacitor of oil charging up and then discharging very quickly and producing this magnetic kick. But then afterwards, you see that you have these eddy currents which persist. And those eddy currents effectively manifest themselves as another contribution to the magnetic field. So we have to understand those particularly well. And so we did that. We made a special device to measure it. The other effect that we have is we pulse these quadrupoles with this 18 kilovolts. When you pulse something very quickly, it basically, when you stop, it starts vibrating. And something vibrating in a magnetic field contributes to another magnetic field. So these plates were vibrating, and that also contributed to the magnetic field. So we had to measure both of those effects very precisely. And we had to create special measuring devices to measure it. So this is the contribution to the magnetic field due to this pulsed electric field. And so it changes over quite a long period of time, but our muons are only here. So we had to create a special device that we could put in and measure that. So we measured that. In the end, it turned out the contribution was very small, like 20 parts per billion, but we didn't know until we measured it. And the uncertainty was basically as large as the correction. And the eddy currents, we also had to create a couple of special devices to measure it. And again, the correction wasn't particularly large, and our two devices essentially gave a consistent picture. So we took data over about 5 years, including an interesting period of COVID around here when we shut down like everybody else did in March 2020. But we had some problems in the early data, but everything got. And here we didn't take so much data because we were largely doing systematic studies rather than trying to accumulate statistics, because we already knew we had enough statistics. So essentially we met our goal. This is the only experiment I've ever been on where before you start the experiment, you have a goal of what you want to achieve. And we amazingly achieved it. And we actually achieved it within about 2 or 3 years of the time we said, whereas most experiments tend to be late and often don't achieve their goals. So we then did lots and lots of systematic checks. We did about 100 systematic checks. The systematic uncertainty is 76 parts per billion. There's no real one great contribution to that. It comes from, these magnetic field corrections, these momentum, dispersion in the momentum corrections. But again, we got to 76 parts per billion. Our aim was 100, so we achieved our goal, which I think was a surprise. And then I come back to this thing where I said we had this magic offset in an envelope, and we only wanted to know what we would say. Our analysis is finished. Tell us the number, because you don't want to be biased and go, just tell me the number. And you go, oh no, I don't really like that answer. And you go back and analyze it. You can't do that. So the original Brookhaven experiment, which we largely mimicked, made this measurement. They had a problem with their envelope because it was in somebody's office. He then moved office or retired, and the overzealous cleaner threw the envelope away, and they went, oh God, we've been taking data for 4 years, and now we can't release it because we've lost the offset number. And so enter the PhD student who had to go into all these dumpsters in Boston and ferret around for half an hour and found the envelope. Thank God. So they found the envelope and did it. So, and then when we unblinded this result, this was in Liverpool. This is my friend James Mott and my friend Joe Price. You'll see this paper is looking a bit dishevelled. That's because good old James Mott decided to go around Liverpool the day before and get very drunk. But it was raining, but he had the envelope in his pocket, and it very nearly disintegrated in the Liverpool rain, so that had to be opened very, very carefully. For this one in run 6, we had no envelope problems. I'm pleased. It was a seamless operation. We had no problems. So you can see there, that's the results, basically. After all this work, they measured it that well, and we measured it that well, right? So we've improved the precision by about a factor of 5. We did some consistency checks of dicing up the data by different run periods and different run conditions, and the chi-squared is very good and also is consistent with the previous measurements. Also, with slightly different magnetic fields, you expect these things to go on this line, which if you average these, you've got a point about here and a point about there, so that's broadly what we expected. And then, how many years have I devoted to this in my life? About 14 years of my life. You get one number. And that's the number. It's a bit sad, isn't it? That's the number. That's the uncertainty. So it's 414 to 417 or 411. And then the only point of this is you have to have a prediction for what these virtual corrections do from the strong interaction, the weak interaction, the electromagnetic interaction. And then we need our theoretical colleagues. And there is a problem calculating the contribution of the strong interaction. So 4 years ago, they did a prediction, our theory colleagues, and it was this. And so then the difference between our measurement and this is 5 sigma, and everybody would be going, oh, great, we should go to Stockholm and collect our Nobel Prize. But then the theorists went, whoa, we don't know what we're doing, and decided on a completely different method of predicting it. And the difference between these is now 3 standard deviations. So the theory doesn't agree with itself at 3 standard deviations. You'll notice here that all the actions basically in about the 9th decimal place, right? So this is, you know, the 0.0023 is predicted by alpha over pi, right? Mr. Schwinger predicts that perfectly. But this is the most precise measurement ever made at a particle accelerator. Of course, the BBC and people only look at this number and not this number, and then they get very excited, and then they put people like me on the news or whatever and say you've discovered a 5th force, and you go, oh, it's not as simple as that. And they go, don't say that, we just want a story, just say it's great, etc., etc. So obviously it's not as simple as that, right? So this is the mess that we have at the moment. As experimentalists, we've delivered our pledge to improve the measurement by about a factor of 5. These are the theory determinations. These in green are the one method of determining the theory. And you can see they largely agree, apart from this point, which doesn't agree with its previous measurement. So this is not good. And then this is the new way of calculating the theory, then jumped over here using something called lattice QCD. So you can see this is about essentially the full range of theory predictions. So if you were being, I would say, being honest, what you would say is the theory is about here with an uncertainty about this big. But they didn't want to do that because it doesn't look good, right? So they decided they'd say that. So anyway, this is going to take, I would say, 3 or 4 years to resolve. So coming back to our great Francis Farley, here he is. He was a very, very interesting character. He actually, as I said, he went to Clare College, and during the Second World War, he was sequestered out to work on radar. He was a genius. And while he was working on radar, microwave frequencies, he realized that radar, these microwave frequencies, was great, and he could warm up his lunch in the radar. And so essentially he invented the microwave oven, but he realized that this is good. I'm heating, I'm warming up my lunch in my equipment, but then didn't bother to punt it out further, and he sort of regretted that he didn't become a billionaire with the microwave oven. But his this is the way I like to think about all of this, right? Because everybody gets upset. They go, oh, the theory's this, the theory's that, they're different, your measurement's different, what does it mean? And I actually just take it a bit more philosophically now, that basically it's a miracle that this experiment works, given all these things that you have to bring together, and you're controlling things at a nanosecond, and we're making a measurement at 0.1 parts per million. And the theory is actually doing a prediction of order 1 parts per million. It's just that we would like it to be a lot better than that. But I think we shouldn't forget that that's the most astonishing thing. You know, part of this calculation involves 12,762 diagrams, right, to calculate the electromagnetic contribution. So, unfortunately, so that's largely the end of the story. I'll just mention a couple more things of what I'm thinking of doing next. I'm also doing axions as well. But if the muon is behaving strangely, maybe it isn't, let's wait for our theory colleagues, then actually I'm interested in making a measurement which doesn't rely on theory. I don't want to be at the mercy of theoretical physicists telling me this is the prediction, this is your measurement. I want to just measure something which doesn't rely on theory. And there are two things there. The standard model predicts that the electric dipole moment of the muon is immeasurably small. It's like 10 to the minus, what's the number, like 35 or something like that in the magic units. So if you measure a non-zero magnetic electric dipole moment of muon, you've seen some new physics. The other thing is that the standard model predicts that all muons decay and they emit neutrinos, right? Essentially 100% this, but a small fraction like this, right? But if you observe a muon decaying without a neutrino, then that's new physics. And there are predictions of that. So the experiment I'm involved in at the moment is trying to look for the neutrinoless conversion of a muon into an electron without it emitting a neutrino. So to do that, we have to... Oh dear, what's going on here? Oh, yeah. So we built this rather elaborate experiment at Fermilab. Again, we're due to take data in a couple of years. It's a whole suite of magnets which basically funnels muons to a little aluminium target. Here actually comes in this way to this aluminium target. And then we're looking for the positrons just here. And if there are no neutrinos involved, those positrons basically have the mass of the muon. And we have a suite of detectors. But we're looking essentially for what we're producing 10 to the 10 muons a second. So remember in G-2, we're producing 10,000 muons, well, you know, a few tens of thousands of muons a second. Here we're producing 10 to the 10. And we're looking at 1 in 10 to the 18 to decay in a strange way. Somebody told me, I'm from Blackpool, and somebody said that's like looking for 1 grain of sand on Blackpool Beach. But I think I then did the calculation. That was nonsense, I think. But anyway, I'll leave that to you great young minds to work out what 1 part in 10 to the 18 is. I don't think that can possibly be true, right? Anyway, but it's the lowest sensitivity to a single decay of any accelerator-based thing. So I like to do these things which are difficult. The other thing that we want to do is sort out these theory things. One way we could do that is to bypass the theory and just measure muon electron scattering. That basically gives us a theory prediction for what the G-2 is. So it's an experiment which will probably take data at CERN in about 3 or 4 years' time, which is going to measure very precisely muon electron scattering. The details of that are a bit arcane, but that's one way we can get to the theory prediction. So really, my conclusions are really along Gerlach, really, that all of you should never believe theoretical physicists when they say something is not worth doing, because either we know the answer, turns out then they don't actually know the answer because they'll change their mind, or they're wrong, right? So do not believe people who say that something is so obvious that you shouldn't measure it. You should go off and measure it. So over 60 years, we've gone from 4,000 parts per million to 0.1 parts per million. We've now reached the most precise measurement made at a particle accelerator. And like I said, I think unless the LHC shows up some magic particles quite soon, possibly our only hope of discovering physics beyond the standard model is by doing these very precise measurements and looking for tiny deviations. And of course, you never know whether that deviation is significant. You start off with something like this, and you don't know, but you keep digging. So that's all I've got to say, I think. Thank you. And I'm happy to answer questions in a pub or over dinner or whatever as well. So. essentially, essentially if it's got substructure, right, or these virtual diagrams can create an electric dipole moment, and if you put in, and even in the standard model, the muon has an electric dipole moment due to these virtual diagrams, but it's absolutely tiny, and the diagrams are crazy, right? I mean, they don't look like anything you've ever seen before, right? They involve all sorts of loops and gluons in the loops, etc., right? But if you throw in standard model particles into some of those loops, then that 10 to the minus 34 can become 10 to the minus 20 or something like that, right? So if so where people are designing experiments to try and look for a muon magnetic moment, electric moment, EDM at that level, right? Yeah. It's only if you have additional non-standard model particles that it gets larger. But it's a difficult measurement. Basically, how you measure it is we're measuring oscillations in one plane in G-2. You see vertical oscillations, which are on top of the oscillations from the simple harmonic motion. Yeah. Oh God, this is in American units. About 10 to the minus 8 torr. Yeah, that was a problem because, as I say, these chambers we built in the UK were these straw chambers. They had gas in them, and those straws were slightly porous. And so every time the vacuum was bad, they would blame us, going, "Your crappy little straws are leaking." And we went, "It's not us, it's not us." And it turned out it wasn't. There were leaks, Yeah, it's hard to keep that vacuum. Yeah.
I'm just surprised how big it is and such a good vacuum.
Yeah, no, it was hard work.
Yeah.
So obviously everything you put in, you have to clean incredibly. And actually, and it takes a while to get that vacuum down. I mean, it would take days for the first time you do it. But then every time we'd have to pump up to atmospheric pressure, we'd make sure that nobody went anywhere near anything unless everything was spotlessly clean, right?
I see. So how many days did it take?
Initially, to get it down to, when we first started taking data, weeks, right? Yeah, but then eventually, once we'd got rid of all the crap, because also what happens is there's bits of crap, right? And then the electric field will burn off some of the crap, and even the beam will move some of the crap, right? And then the vacuum pump it out, right? So eventually, you've got rid of all the crap inside your ring, right? But that took weeks.
Do you need to heat it up?
You can do, yeah. That's what we did. That was the first thing, yeah. You bake it out, yeah. So we had big problems as well because when we originally put the ring in the room, it was a brand new room, but we didn't control the temperature was reasonably controlled. But you can imagine in Chicago, it's 30 degrees in the summer and minus 20 in the winter. So we were getting day-night variations. So we had to put basically IKEA quilts over the magnet as well, right? Just to keep it uniform temperatures. All sorts of things happening. Yeah. So that was a bit of a struggle. Yeah.
You said that the direction of the muon spin is the same as the momentum of the positron.
Yes.
But the electron has spin half, and the neutrino has spin half.
Yeah.
It could be like.
Yeah, no, so this is a subtlety of the weak interaction. There's a difference between helicity and chirality, right? So you believe the neutrinos have to be produced with the spin opposite the momentum, right? But then when you try and conserve momentum, it forces your electrons into slightly unnatural configuration, basically. But so the way you can do it is the highest momentum one. It only works when you draw the diagrams of the highest momentum ones. The spin is for the positrons is not actually the way you want it to be, right? But it's the way which conserves spin. It's well defined. It's very well predicted what the configurations of spin and momentum are, basically. At the at some level. I mean, yeah. So it's part of the structure of the weak interactions. Has got this in Dirac matrices, the gamma mu 1 minus gamma 5, right? There's this V minus A in the weak interaction, right? And it's basically that which determines the momentum and spin directions. So it's not. It's only perfect in the extremes of the muon at rest and the the highest energy positrons. But you can predict what happens at all momentums and what the correlation is. How? Oh, it's very boring. Because you just have particles spraying out at all different momentums, and you just have some magnets, and you know that if it's going through those, it's that momentum. So it's just collimating by magnets. It's not very sophisticated. Well, I say that. I mean, it's you know, they've got to work, and you've got to focus it as well, right? And I mean, also one of the other problems is we're producing not all pions decay at the same time, right? I mean, they've got a pretty short lifetime, 20 odd nanoseconds, whatever, but they're not all decaying at the same time. And your muon spin is also determined from where, the direction your muon spin is pointing in initially is determined from your pion decay as well. So it's the case that all your muons aren't all perfectly, say, going that way, right? Some are going that, so that's one of the effects that we also have to correct for, which is, annoying. But that's a reasonably small effect, but that's quite subtle, and that took us about nearly all, some of these systematic effects, these corrections, some of them took months or years to work out. Yeah. Yeah. I wouldn't use the word perfect in anything to do with experiment. Yeah, no, it's pretty good. Yeah. So mostly their timing resolution was good as well. So it's often the case that you can get detectors who have good energy resolution and lousy time resolution, but these also had good time resolution and sufficient energy resolution. Yeah.
But for this experiment, do you need a wide enough?
No, because essentially we're only measuring 1.6 to 3.1 GeV energy positrons. So most calorimeters, like at the L8C or whatever, are measuring things which are hundreds of GeV, right? So we're a sort of unique calorimeter that we're measuring relatively low energies, so it had to be a certain type of design, which was good for low energies, but wouldn't be very good for high energies. It'd be terrible for high energies, actually. It's not big, because it wouldn't be big enough, the particles wouldn't shower in the volume. So, so it was largely built bespoke for this experiment, that calorimeter. So that was built by the US team in Washington and Seattle. They did a great job. Well, no, it's an array of crystals. There's 54 of them. It's an array of 9 by 6, and each one of them's about this big and about that long. No, it's beautiful. When you look at it, it's beautiful, right? It's like, yeah. Well, it's not. I mean, it's. Have you seen the L8C calorimeters? A single module is way bigger than that. Right. Right, yes. Sorry for going on. Yeah.